Let's consider another thought experiment, um, which will demonstrate to us how the idea of how the time flows is not an absolute one, but it's a relative one. So to do that, let's consider a spaceship in which there's an astronaut and then there's a light source and on the ceiling there's a mirror. So you can emit a ray of light upward and then it bounces back from the mirror like that. So the astronaut sees the ray of light going up and then coming back down. Let's say the distance between the mirror and the light source is d. And now consider an observer on Earth looking at this same phenomenon, namely light being emitted from the lamp, going up, and then being reflected from the mirror, and then coming down. Now, the spaceship is moving, let's say, to the right at a velocity v. So for a person on Earth, what the person on Earth will see is the following. It's going to be like a movie. You have ray of light going up and the spaceship moving to the right at the same time. So in the first frame, I will consider the motion of the light beam in the upward direction, and then it's going to get reflected, and then it will come back to where it started. So what the person on ground sees is the following. A ray of light, instead of going straight up, will be going at an angle because of the motion of the spaceship to the right. So the motion is not just up and down, but it's also up and right. And then here's the mirror. And then that beam of light or ray of light gets reflected. And then the same thing on the way down, as the ray of light is coming down, the spaceship is moving to the right. So that's kind of what happens there. So it ends up here, it starts over here. So as you can see, the distance covered by the ray of light as seen by the astronaut is shorter than what is seen by the observer on ground. The distance as seen by the astronaut is just d up and d down, so 2d, whereas at the bottom it's more than 2d. So we are interested in exploring this difference in a little more detail. So let's call delta T naught the time measured by the astronaut, and delta t is the time measured from Earth. So if you consider this triangle here formed by the ray of light going up at an angle and then coming down at an angle, in that triangle, the height is d, and let's say this side of the triangle is s, this is also s. We expect this to be an isosceles triangle because of the symmetry here. And let's say that during that time that the ray of light goes up and then bounces back down, the spaceship has moved a distance 2L. So first of all, since the spaceship is moving to the right with a velocity v, we expect 2L, which is the distance covered by the spaceship in a time delta t, to be equal to v delta t. Remember, delta t is the time measured from Earth, and this triangular sort of path is also that's what's seen from Earth. So this equation represents what's being observed from Earth. So the distance traveled is v delta t over 2. That's the distance traveled as seen by the beam of light as seen from Earth. Now, the distance traveled as seen by the astronaut is just 2d. The distance as seen by astronaut is 2d. And distance as seen from Earth is basically s here and then s here. So 2s. Okay, let me go back to my notes. This will be more legible. So it's basically the same diagram I was trying to make. So I had gotten this far. Distance traveled as seen by astronaut is 2d. Distance traveled as seen from Earth is 2s. So basically delta t naught, time elapsed as measured by astronaut, is distance divided by speed. Now we are talking about light here. and distance as measured by the astronaut is 2d, the speed of light is c, so delta t naught should be 2d over c. Similarly, time elapsed as measured from Earth is also distance over speed, so 2s over the speed of light. Now notice one thing, that speed of light is being taken to be c in both these equations, meaning the speed of light for the astronaut is the same as the speed of light as it is for an observer on Earth, which basically comes out of the second postulate of Einstein's relativity, that the speed of light remains constant, remains c, no matter who's observing it from what frame of reference. So going back to this diagram that you can see from this triangle, if you split it into two right triangles, you can see that S equals square root of d square plus L square, and L was V delta T over 2. And so you can write it as square root of d square plus V delta T square over 2. And if you simplify it, it becomes 2 times square root of, I'm using these two equations, delta t equals 2s over c and s equals square root of d square plus L square. So if you substitute the second equation into the first one, you get this. And so delta t is 2 times all that. When you square both sides, delta t square is 4 times d square plus v square delta t square over 4 over c square. And then you keep simplifying it, and delta t square then is 4. If you distribute the 4, you get 4d square over c square, plus the 4's cancel out in the second term, so you're left with v square delta t square over c square. And then the first term, 4d square over c square on the right side, is basically the square of 2d over c, 2d over c, which, as you see here, is delta t naught. So it's the square of delta t naught. So that 4d square over c square can be written as delta t naught square, and then plus that. Now you have two terms that contain delta t, the one on the left and the second one on the right. You bring both of them to one side and factor out delta t, and which basically leads you to this equation. Delta t equals delta t naught over square root of 1 minus v square over c square. 1 minus v square over c square. Now this factor, 1 over square root of 1 minus v square over c square, appears quite frequently in special relativity. And to keep things brief, we give it a symbol. We use gamma to represent square root of 1 minus v square over c square. So in terms of gamma, you can write this equation as delta t equals gamma delta t naught. Now, gamma has to be greater than 1. As you can see, the velocity of the spaceship has to be less than speed of light. Nothing can go faster than speed of light. So this is going to be, the denominator is going to be a number which is less than 1. You subtract 1 minus something less than 1, you're going to get a number less than 1, even if you take the square root of it. So gamma is less than 1. And what that means is delta t is always going to be less than delta t naught. So delta t naught is called the proper time, which is the time measured by observer at rest. So that in this case would be the astronaut. At rest relative to the event being observed. In this case, the event is going up of the light ray and then being reflected back. So the subscript 0 naught is used for that observer with respect to whom the event is taking place at rest. So delta t naught is going to be less than delta t because gamma is greater than 1. And this is called time dilation. So when a phenomenon is occurring in a frame of reference that is moving, time appears to be going slower. It stretches out. So essentially, the flow of time as measured by the astronaut is different from the flow of time as measured by the observer on ground. It's not a matter of right or wrong. It's not that one is more correct than the other. It's just the nature of physical reality, that the time as measured by the two observers flows at different times. So that's the second consequence of the two postulates of relativity. The first one was simultaneity being relative or not being absolute, and then time dilation is the second one. Um, a couple of lectures before, I'd said that if the speed involved is much less than speed of light, then the equations of relativity revert back to what the classical relations are. So let's consider two extremes of velocity. One, let's say the spaceship was going very, very close to speed of light. So as v approaches c, gamma would approach infinity. Because if you look at gamma, as v approaches c, v squared over c squared approaches 1, and the denominator approaches 0. So gamma is approaching infinity. If gamma is approaching infinity, then delta t is approaching infinity as well. So as the spaceship moves closer and closer to the speed of light, the time interval measured by the by the observer on ground approaches infinity. What does that mean? It means that if the spaceship is traveling at speed of light, the time in the spaceship as seen from Earth would stand still. It would take an infinite amount of time for the ray of light to go up and come back down. So it's almost like time is standing still. Let's consider the situation if v was greater than c. So if the speed of the spaceship was bigger than the speed of light, what happens mathematically in this equation? If v is bigger than c, you basically in the denominator are going to have the square root of a negative number, which is, imaginary. So if the spaceship was going at a speed greater than the speed of light, the time as seen by observer on Earth will become imaginary. And that obviously is ridiculous in terms of physical reality. So the only conclusion you can draw from that is nothing can go faster than speed of light. The other extreme, if v was much less than c, then what happens? If v is much less than c, in this equation of time dilation, the second term becomes almost zero. If v is much less than c, the denominator is just pretty practically 1. And if the denominator is 1, then delta t is equal to delta t naught, which is a classical result that the flow of time does not depend on who's observing the event. So if v is much smaller than c, gamma approaches 1 and delta t approaches delta t naught, the classical expectation. So all time intervals seem longer, or clocks, including biological clocks, slow down, as seen from Earth. So from Earth, an astronaut would appear to be aging less. Now, this may seem like something magical, but there is actually considerable experimental evidence for time dilation. It does actually happen. It is real. One of the natural phenomenon that sort of strengthens the idea of time dilation is the following. Earth is constantly being bombarded by what are known as cosmic rays. Cosmic rays are basically ionized particles shooting towards the Earth from outer space. Now, when these cosmic rays, when these ionized particles interact with nuclei in the upper atmosphere, the nuclei in the atoms of the molecules that make up the upper atmosphere, in that interaction, there are some unstable particles called muons, which are produced. And these muons have different speeds. Muon being an unstable particle means they only live for a certain period of time, and then they decay, they disappear, or they convert into other particles. The decay rates of muons as measured from Earth are consistent with delta t equals gamma delta t naught, or the moving muons decay more slowly. The moving muons decay more slowly. Let's look at problem 4. So in problem 4, suppose a particle called a kaon is created by cosmic radiation striking the atmosphere. The kaon moves by you at 0.98 C, and it lives 1.24 times 10 to the negative 8 seconds when at rest relative to an observer. How long does it live as you observe it? So in a lot of the relativity problems, the principal task or the principal hurdle to cross is to identify which quantity will have the subscript of 0 and which will not. So remember, the subscript naught or 0 is used for things observed from rest relative to the event that's occurring. And the ones that don't are the things measured by an observer who's moving with respect to the event. So if you put together all of the variables in problem 4, first of all, the particle is moving at 0.98 C, so V is 0.98 C. Secondly, you have a time of 1.244 times 10 to the negative 8 seconds. Now we have to decide if this is going to be delta t or delta t naught. Now they specify this is the time measured at rest relative to an observer. So if the particle was at rest, it would live to be this long. So clearly, we are talking about delta T naught being 1.24 times 10 to the negative 8 seconds. And we have to figure out how long does it live as you observe it. So we're looking for delta T. So basically, we use the time dilation equation and solve for delta T. In a lot of these problems, you'll see that the velocity v is given as a multiple of c. It makes the calculations easier because v here is 0.98 c, and then you have a c in the denominator, so the two c's cancel out, and you're just left with the square of 0.98 here. Anyway, so the net result is delta t is 6.23 times 10 to the negative 8 seconds. So if the particle was at rest with respect to you, it would appear to have a lifetime of 1.24 times 10 to the negative 8 seconds. But if it was moving at 0.98 c past you, you will measure its life to be greater than that, 6.23 times 10 to the negative 8 seconds. One last topic in this section is what's called the twin paradox. So the idea is as follows. Let's say you have two siblings, twins, one of whom gets on a spaceship and takes a journey to the outer space and then eventually comes back. Now, when the spaceship is traveling away from the Earth, the person who remained on the ground sees the spaceship moving, and therefore the twin in the spaceship aging at a slower rate than themselves. Which means you would expect that when the spaceship comes back, the twin on ground would see their sibling to have aged less than what they have. That in itself is pretty strange, but the actual paradox here is something more strange than that. Now, when the spaceship is going away from the twin on Earth, as seen by the astronaut, as seen by the twin on the spaceship, the twin on Earth is moving in the opposite direction relative to them. So it's not just the twin in the spaceship who's moving away from the twin on ground, but also the twin on ground is moving away from the twin on the spaceship. So if the twin on spaceship measures the aging of the twin on Earth, they would also measure a slowed down aging. So the astronaut, upon their return, would expect the twin on Earth to be younger, whereas the twin on Earth expects the astronaut to be younger. So they both have contradictory expectations, and hence this is what's called the twin paradox, like which one of them is true. Now, the way you resolve this paradox is by observing that the spaceship does not constitute an inertial frame. There are several instances during the motion of the spaceship that it's being accelerated, and therefore it becomes a non-inertial frame. Obviously, the spaceship will begin at rest and then accelerate to a certain speed. So there is acceleration. And then before it returns, it will have to be stopped at some point in outer space to reverse its direction of motion. So there is another acceleration. And so it stops and then speeds up again and begins to move towards the Earth. That's another acceleration. And then when it reaches Earth, it has to stop on Earth. So that's one, two, three, fourth acceleration. So essentially, this is the spaceship does not constitute an inertial frame. It's a non-inertial frame. And so results of special relativity do not apply to this situation. So that's how you resolve the twin paradox. So that was the end of section 2 of chapter 28. In the next section, we'll see how the two postulates of relativity affect the measurement of length.